Okay, good morning all, or good afternoon, depending where you are. Today, I'll be having a look at just facets of the Golden Mile and the land holding in and around Kalgoorlie there. And it's really just some lessons and learnings and, mistakes I've made, but also really it's a fabulous collection of images. We're able to, over the time, get some really good photos of some interesting pieces of rock. So it's just a way of sharing those so people can see it. And if you want higher resolution versions, just give me a yell. You can have them. I've got no dramas at all sharing it. Yep. Alrighty. Okay, just first up, just a gratuitous ad. AJES is planning to do Critical Minerals of Australia special issue. So the call's out for authors. So if this is your field and you want to publish something, because people are very interested right now, get a hold of Carl over at Uni of Adelaide. He's sitting by the phone right now waiting for authors to come through. So do that. I encourage you to do it, and I think it'll be very worthy volume. I certainly like to read it myself. Alrighty, so first up, just a quick summary. Whoop, jumped ahead. There's just a few lessons in here. It's really the story is persistent wins the day, and really that's a lesson you get with exploration wherever you are in whatever endeavour it is, right? So it's you persist when you're hunting down whatever it is, and in this instance in Kalgoorlie, there's such a history of knowledge. It's tracking down what's been done before is the key thing that adds the most value, because somebody's already done it, they've learnt the lessons, and you don't have to go and drill it, you just have to read it, and you're there. So that was a good one. Being clear on what's an observation versus what's an interpretation. This is where I've almost always come unstuck. As an observation is a fact and it's immutable and it just is. And the interpretation is what you make of it and how you predict the future, right? So it's trying to work out that clear difference. And when you're recording things, you need to be clear about what's an observation and what's your interpretation, because that then affects other people in the future. The other trick was routine observations over an enormous period of time helps build a fabulous data set. And if you just keep doing routine, what you might consider boring, simple things over and over and over, that's what wins the day. And finally, my own little saying is trust your own observations, always ahead of interpretations, because the observation should not change, because it's a fact, it's real, it's immutable. Right, so the image we have at the bottom of the screen there is a shot of Kalgoorlie, so north's off to the left, just so you can orient yourselves. The image isn't scaled, but you can easily download this from the GSWA website. They've got GeoView, so it's got all sorts of data there that's freely available. I've just highlighted some locations on the map here, and these are locations that I'll probably talk about, as I drift through the images as we go. A few things that are missing is just off screen to the north is 8 Mile Dam, and just off screen to the south is Faysville. So there are two other locations that I might mention as we go. But mostly it's Fimiston in the centre of the shot, Mount Charlotte just to the left of that, and Mount Percy a little bit more to the left again. And the south end features prominently, so that's down to the right. So the depth of history in Kalgoorlie, just as an example, here's a photo. It's taken from the Eastern Goldfields Historical Society's collection. And also there's another version available through the State Library. And I found both these organisations were extremely helpful at trying to get you in touch with the information you're after. And certainly the State Library kept going there repeatedly through time, and their collection does change with time. So don't just go and check something once, go and check it again and again and again, because the collection grows and the information increases. So we've put together just a little bit, this was one we used to do for visitors to the Golden Mile. It's just a little bit of fun, but it's this image in the 1940s, and then marrying that up with the tunnels and drives and shafts and everything underneath, And then finally with the super pit. So you can just see how that plays through there. It's amazing, like the tunnels and drives there, I think there's something 5,000, 6,000 kilometres worth of underground workings. I mean, you could go most of the way to Melbourne from Perth, you know, underground if that was all in one straight line, right? So it's a fabulous piece of work, embodied work by all the miners over time. But certainly what goes with that is all the geological information that's been gathered, you know, over a century or a bit over a century's worth of time. So firstly, just looking, this is the youngest mineralisation on the field. So it's classic orogenics. This is the Mount Charlotte Stockworks. So it's, in this instance, both photos, it's in the golden mold dolerite, unit 8. So what we have is predominantly quartz veins, and then surrounding quartz veins, you get these clouds of dominantly pyrite, sulfides around it, and then the gold sits within the pyrite or as small inclusions just on the edge of the quartz veins. And as a rule of thumb, if you're looking at, say, like a meter's distance in the wall, so on the image on the right, you want 2 veins per meter, and that would generally pay. So if you get less than that, it sort of wasn't enough grade to carry. And the reason for that is the selvage around the veins, that 2 veins a meter starts to link up. So essentially the whole volume of rock is mineralized, and that's the advantage with it. And it's a good little rule of thumb. Here's another view of a Mount Charlotte style vein. So the Charlotte veins occur throughout all the different rock types in the field. This one, it's sitting up high, up in the Black Flag or the younger Black Flag sequence. And one thing that's typical of the Charlotte veins is they are high in tungsten. So you invariably come across scheelite. So having a UV light when you're kicking around looking at these things is very handy. And this is a pattern that you don't just see around Kalgoorlie, but you see it throughout the Yilgarn as scheelite sitting in these late veins is very common. That's one thing, always thinking about it, but never do anything about it, is you mine these things, they're chock-a-block full of some other mineral that you're not mining. It goes to the processing plant because it's sitting there with the gold. And essentially this is the heavy, so you separate off all the floats. That's where the gold goes, is with the floats with the sulfide. And the heavies go out the back and chucked away. But essentially you've concentrated these heavies. So the scheelite gets up concentrated in that waste and put somewhere. And scheelite, going back to the critical minerals ad earlier, I mean, scheelite matters. It's a very useful industrial mineral. So it's something to think about if you're on a mine site, is what other products are you using or going through? Well, what's there, you know? There's something that could be an added value for your organisation, and it'd certainly be good for our nation. Right, the older of the mineralisation styles we have on the field is the Fimiston Lodes. So here's a few examples here. The one on the far left is in unit 8 of the gold mold dolerite. And the one in the centre, I think from memory, is unit 2 or unit 3 of the gold mold dolerite. So it's much lower down in that dolerite sequence. And the third one is a spectacular piece of gold in there. But I had the smart idea one day, as smart or not, but why not cut the vein longitudinally? So in the plane of the vein, to see what direction you could get the high grade. And so we cut it along the vein, and sure enough, this thing opened up and it was chock-a-block full of gold, and that was just stunning. But it does have a preferred trend tracking within that plane. So I always wanted to try and find a sample that we could orient. So something still in the wall, you could orient the sample and then do the same thing again, and then be able to measure the plunge of the high grade within a vein. Because, you know, trying to link it to the fractal nature of the small scale and the larger scale, would it all tie up? But never got round and pulled that task off. So that still awaits someone else if that's interesting for them. But yeah, just an aside. The green lead is a variation on the Fimiston style mineralisation, and it's really quite striking. When you find a piece of this, it's almost like green glass. It's really quite something. It's very vivid green. So the field term for this is, we call it roscolite. but in reality, it's not roscolite. It doesn't have a high enough vanadium content. So it's probably more akin to a nolanite or a tivanite, right? These are vanadium-rich minerals that are akin to roscolite, but they just have a lower vanadium content. And essentially, it's a vanadium-rich white mica. So calling it vanadium sericite is pretty close, and it works. More often than not, it's a breccia. So this thing has failed, as the structures have moved, and you get all sorts of fragments. You don't tend to get milling or rounding in the clasts. They're always very angular, and you almost always see these banded textures around them. So probably suggesting cyclic activity, and also, probably lower pressures. So the observation is the breccias and the banding. My interpretation was that this occurred near or at the surface and potentially in the epithermal field, right? So arsenic halos are quite abundant in and around the Kalgoorlie lodes, the Fimiston Lodes in particular, and not so much with the Mount Charlotte veins. They're very discrete. But after a while searching, you always go searching for some other document or a map or something in the archive, and then you'd always come out with something completely different. And just one day we were looking for a document and we came across another one that someone from Western Mining had written years back, discussing the arsenic halos. And they'd worked out that the cutoff was about 50 ppm and the distance from the lode was about 50 meters. So you could, if you had a means of tracking your arsenic composition or even just spotting arsenopyrite, that would give you a good indicator that you were tracking in close to a lode. And that was, that's very useful to know. Certainly if you're working regionally and you're looking for something that's akin to this, that would be very helpful knowledge, right? So that was good to know. The other thing we found was quite by accident. I had no idea this existed for many years, but there's a museum attached to Wasm in the middle of town. And it's just a fantastic old Victorian geological museum. And you go in there and there's rocks and glass cabinets everywhere. But there's a couple of examples here on the left. There's the arsenopyrite there taken from the South Kal Gold Mine. So certainly the old boys were seeing it. It's not just a new thing. But the one that was really interesting is this piece of native arsenic. So it's just pure arsenic metal. They got from great depth down in the system, so the 2,500 foot level. That's quite a ways down. So that was really interesting to see. So these samples still exist. They're still in the museum today. And it's easy for you to get in and access, and there's no charge to get in. It's just some fabulous samples there. So there'll be a series of these samples in this presentation because people don't know it exists. They're great samples and they're really quite photogenic. So here's some other samples from the Wasm Museum. And here's some minerals that people don't tend to associate with these large orogenic systems. So we've got orpiment, realgar, pararealgar. So it's the arsenic, antimony minerals. And it's just really, really unusual to get these things in these big systems. And, they're very visual, they're very bright. I remember discussing it one day with some academics, and they suggested that it was driven by weathering of the sulfides that we just been discussing. So yeah, fair enough. But I mean, the samples in this instance, the 1,400 foot level, so probably at about 400 meters, 450 meters down, we're well beyond the range of weathering. I mean, realistically. And also, I mean, these pieces of realgar, if you can see the sample in the upper left there, that's got the arrow on it. I mean, the realgar, or the orpiment in this case, sorry, is very much trapped well within the silicates. It's got no access to air, right? It can't weather. And so these things are being formed with the deposit. So these are Fimiston stage veins. They've got that classic cockade coliform textures, and the silicate in there is a chalcedony. So it has plumose extinctions. So these type of minerals tend to form in low pressure, low temperature environments. So it's really interesting, again, reinforcing the idea that this is a very shallow level system. Here's another sample. This one, geologist that found this one was Chris Buxton. And the original slab was a couple of meters across. So after the geologists were done with it, this is the only piece left. And, you know, it was spectacular. The blades of stibnite were over 1/2 meter long. It was very impressive. Now, I failed to get a photo of the entire slab because it was really quite something. But again, the stibnite reinforcing these unusual metal associations with this system. So you tend to see arsenic, antimony, bismuth, mercury, tellurium, selenium tend to be the friends of gold here in the Golden Mile. And interestingly, when you look at Mount Charlotte, it's gold and tungsten and pretty much nothing else. That's very clean and discrete. Right, one of the big differences with the Golden Mile is the presence of tellurides. So here's a sample. It's a little bit out of focus, but you know, I had to shoot it from a couple of meters away. But this one's held in the West Australian Museum in Kalgoorlie, and it's in a giant safe underground. So it's, you know, it's a bit of, not too much of an effort to see it, but it's difficult to photograph. But it's fairly classic of the tellurides when you see them. They look a bit like sulfides, but not quite. And they tend to have these sort of conchoidal shapes, or the crystal structures themselves appear bent or stressed, or they just seem a little bit different. And you just sort of, oh, you know. So they are difficult to identify. After a while, you get your eye in and you get really good at it. And, you know, we had a crew there that was able to do it with ease, but now I just can't remember all the different features of each one, and just it slides with time. So it's same thing with most geological pieces of knowledge. Once it's in your head, it's it decays with time. You need to write it all down. So looking into more of these samples that are hiding in and around the museum at Wasm, there's a lot of sulfates, and there's a lot of sulfates in the Golden Mile system. So barite is intergrown with the Fimiston ores, and also we see celestite, which is the strontium sulfate. So the celestite is almost always in big vugs and in late structures. And the interpretation is the strontium's being up concentrated by the recrystallization of gypsum. So there's quite a lot of gypsum in the system, or gypsum anhydrite. So you release the strontium there, and then it recrystallizes its own mineral, celestite. So it's not, you don't really see the celestite grown in with the Fimiston ores. It's almost always in a vug, a late open vug that's still open today, right? So anhydrite is really interesting. So these are 3 examples. It's everywhere in the Fimiston system. I've seen it in a lot of the other systems throughout the Yilgarn as well, the big mines. Anhydrite's a key part of the assemblage. So there's chock-a-block of sulfides kicking around those systems, and it's almost always associated with some sort of banded veining. So the composition's changing, and the deposition process is probably cyclic as well. So that's interesting. So in these 3 examples here, it's all within a dolerite host, the Golden Mile dolerite. On the left, SE19, that holds, it's held in the GSWA collection, and so is WDD3. That used to be a very deep hole on the Golden Mile. And MM3, I can't remember where we drilled that one, but it was in Fimiston itself. But interestingly, the sample on the left, in SE19, you can see association there with a manganese carbonate. So that was interesting in its own right. And you'll probably hear me talk a little bit about manganese just in passing. It's just an interesting aside. There seems to be a bit of manganese kicking around, and it's going into these unusual minerals. So it's probably part of the story. How that links in, I never ran that to ground, but it's certainly fascinating, right? But anhydrite, almost always linked with the carbonates and sulfides. I remember there were some rare occasions when we found visible gold actually in the anhydrite veins. So they're certainly linked with the mineralizing event, and timing-wise, through cross-cutting relationships, they sit in neatly with the Fimiston style mineralization. This was an interesting sample, Albite Veining. So that sits in the museum. So certainly feldspar veining is not uncommon within the Fimiston system. So there's a number of different feldspars kicking around, and it does surprise you when you realise they're in there. And I remember one time when we were logging, thought we had some unusual quartz veins, and it wasn't until the light caught the core at the right angle, and I realised that it was full of cleaved. The minerals were cleaved, and quartz doesn't have a cleavage. I was like, oh, okay, so I need to work on this. So it took us a couple of days running it to ground. It's not carbonates. Did a whole bunch of tests. And this is before we had the X-ray guns that could tell you straight away what you're looking at, but you had to go through and work the problem. And we ended up, look, we're dealing with feldspar veining. It's like, okay, well, it's just an alteration. And again, cross-cutting relationships placed it in with the Fimiston style event. So it's really quite an early part of the mineralizing system. And it's interesting in this instance, the feldspar is lining a vug, and it's quite an open vug. So it's either this is a Fimiston vug that's survived, or it's a later vug that's got some recrystallized feldspar in there. So it's neat. The chloritoid alteration is quite a good story. So this example is what the old boys called calc schist. So the new terminology, that's Paringa basalt. And the chloritoid in it are the dark black to green sort of spots that sit within that rock mass. So chloritoid's a bit of a halfway mineral. And what generally happens if you've got an iron-rich rock like a basalt, and then you alter it, so you have to alter it first before you metamorphose it. So you generally, it goes to carbonate, sericite, whatever. But then you get a high iron rock, you alter it. So essentially you start washing out the other metals and you're up concentrating the aluminium content. And then you metamorphose it. The rock doesn't have a lot of places to go with regards to minerals. So it crystallizes everything out, and whatever's left over, it ends up as the chloritoid. So this is not generally something well understood here in Australia. And I only cottoned onto it when I was working in Canada, because the Canadians, they're all across this, because their VMS systems in their footwalls are chock-a-block full of chloritoid. It's like, oh, man. So once you understand that, it's like, right, we've got this huge alteration system at Fimiston, and the footwall to that, so the Paringa basalt on the eastern side, is just flooded with chloritoid. And it was quite by chance that someone had mentioned they'd seen chloritoid, and I'd had a previous experience with chloritoid drilling a deposit called Just In Case, which became Wallaby. And we had this unusual rock we called spotted rock. And the spotted rock, we didn't know what it was, sent it off for a thin section, it came back chloritoid, didn't know what to do with it, had the VMS experience, and then forever after that's like, right, I'm on high beam for chloritoid. We came across a document, and it was just a fragment of a map at the Historical Society. It was a geology map, and it had a mention of chloritoid alteration. So like, it had a date, it had an author, righto. So then went to the other archive at KCGM and went hunting for it. And we found another map. It was much larger scale, and it had chloritoid locations all over it. It was done by Western Mining. And the GA behind the project was Rex Prider. So he'd written a paper on the presence of chloritoid in the Kalgoorlie field. So it's really interesting. It's part of the story. I'm sure the guys on site now are right across it because they're a pretty smart crew. But that's a really interesting part of the story. So here's a section through a series of the Paringa basalt pillows. This is taken out of the Fimiston pit. And within that, you can see the chilled margins of those pillows. And within that, you see the darker spots. And the darker spots are concentrated in the chilled margins, but you also see it going into the central mass of the pillows themselves. And these are the grains of chloritoid. They just tend to form these darker spots in your rock mass, and everything else gets blasted off to chlorite and white mica and whatever else, right? So that's what it looks like. It's really quite subtle, but once you've learnt to spot it, you can't unsee it. Yeah, so it's a particularly good example of pillows. And that image was scanned at a really high resolution, so it's really quite fabulous. So again, we sent samples off. Here's an example from SE19. So the data from this drill hole's in a WAMEX report you can get from the GSWA. But that's what it looks like. So that in this instance, the pillared basalt, and the pillared basalt sits at the top of the golden moldolorite. The pillared basalt been converted to just about white rock, that just had spots in it, and the spots being chloritoids. So there's a thin section on the right, and that was done for us by Minerex. And the lats of chloritoid just sitting there in this huge mass of essentially white mica and carbonates. Now, so just to make it simple so people can see how that plays out, you generally have your pillared basalts, and they'll have radial and concentric fractures, and that's where the fluid gets in and tracks along these breaks, right? So at the first sort of stages, it's weakly altered, you'll tend to get the chloritoid forming around the outer edge and along the fractures. And then when it's moderately altered, it's throughout the rock mass. And then finally, like that last image there where it's quite pale, the basalt textures, the pillows, are completely undiscernible. And what you do see is you still make out the pillow textures, but it's because of the concentration of chloritoid running along what used to be the fractures, and generally in a white rock. So that's quite amazing when you see a rock that's completely blasted and it's got the chloritoid. You know what you're dealing with. It's an aluminium or periluminous rock that was iron rich, and it's been metamorphosed. Yeah. It also tells you a very interesting thing about the mineral system, and that the mineralization and the alteration occurred before the metamorphic event, because all that had to occur first to be metamorphosed. Right, golden mold dolerite is the bread and butter really of the Fimiston system. It takes up the lion's share of the pit, and also it's really the holy host. That's what carries most of the gold and most of the grade. So the big hitters with regards to where you want to be is unit 8's the favoured unit. This is the one that is the quartz granifier. It tends to be quite brittle. It's full of magnetite and very reactive. Unit 7 is chock-a-block full of magnetite, and it's also a really good host unit. It just doesn't fracture as well as Unit 8. And then on the other side, Unit 9 is again a very good host, but just not as good as Unit 8. So it's interesting to note the unit that carries the most gold is Unit 9. Unit 8 carries the higher grades. So it's just interesting. You'd sort of think that, oh, everyone focuses on Unit 8, but the real money maker is Unit 9. Yeah. So just here looking at the work done by Western Minings. This is Travis Woodall and Bartram in 1971. And it's a schematic section through the gold mold dolerite, and it's showing all the different variations in some very useful elements and seeing how that plays out. So we did an exercise. We went and found some old drill core at the government core library at the GSWA. This was the old Western Mining South End drilling. So we pulled those drill holes and we resampled them for multi-element geochemistry using 4-acid. And yeah, we got some fabulous results. I remember going through this data set with Scott Halley just after we'd got it. And I think he was really quite enthused seeing the interplay of the different elements and also marrying that up with the magnetite and what was happening there with magnetite. So I must ask him about that. That's a good reminder. But yeah, I remember going through that with him. It was really enjoyable. Yeah, but those data sets are available, and anyone else can do it too. Just get it out and have a look and see what's going on. But the big hitters in there, it's the formation of magnetite. So you see it kicking in, or the iron oxides. It's a good proxy. You see it kicking in around Unit 6, peaks in Unit 7 and Unit 8. So this is really what drives a lot of the chemistry, is the magnetite. So the lower contact of the gold mold dolerite, it was really hard to find a decent sample of this. And in drill core, it usually shears out or breaks or snaps, right? So it's quite a, not very coherent boundary. It lets go. But this is one sample we got from near, it was near the northern end of the pit, just as we'd mined through the base of the Hinchcliffe lodes. And this one here, you've got the gold mold dolerite, or in this instance, the upper portion of it here. It's a basalt, so that's Unit 1 of the gold mold dolerite is basalt. So it's chilled against the lower sediments. And the sediments underneath, you can see are altered. So these are sediments that we'd refer to as the Arroyo Shale. And they've been altered and they've been baked, hornfelsed. So they've seen the heat from the overlying igneous rock, right? On the upper contact, it was really quite interesting. So it always accepted that these dolerites are silts, and that's how the world was until I saw this hole. So we're going through this hole for other reasons. We're trying to track the geology and pull together the model as we went to the north. But in this instance, we're going through the gold mold dolerite, and then all of a sudden, it just gently grades up through into basalt, and then pillow basalts, and then sediments on top. Quite happy. And that just surprised me. There's my notebook on the bottom right there from the day. I was surprised. It just very unexpected. But on that day, my view of this rock changed, because it now had the possibility that it wasn't just some deep intrusion. This is quite possibly a flow on the Earth's surface. And the timing of it puts it very close to the formation of the Fimiston Lodes themselves. So potentially the magmatic system that's forming this dolerite was also driving the mineralizing event. But that's an interpretation. Yep, the observation holds true. The top of the dolerite in this instance is pillowed, and it's essentially intruded water. That's not an isolated occurrence. Here's another example. So this is a South End hole, so SE2, so it's in the government core library, so it's freely available for everyone to view. So example here, so dolerite on the far right, grading into fairly massive basalts and then into pillowed basalt and hyaloclastite. So it's again the same pattern, the top of this dolerite showing evidence that it's quenching into water. Here's a variation on theme, so it's not so much, it's a basalt, but we've got a conglomerate sitting on top of the dolerite. So this whole LNGD7 from memory is at the south end. The lower part of the screen, it's very clearly dolerite, it's intact, it's igneous rock. But as it passes up through the core tray there, it becomes conglomerate, and finding the boundary was really difficult. In fact, from memory, I don't think we were able to work it out. We just knew the bottom was dolerite and the top was conglomerate. So looking at that there, do you see clastic materials very clearly in the top tray or the top run of the tray? And as you come down, you still see clasts in that mess of rock. So there's large clasts and there's small clasts, and a lot of them are made of the dolerite, the underlying dolerite, and they're just sitting on top of the dolerite itself. So the dolerite had formed as an igneous body, whether it's a flow or an intrusion. There's no way of knowing in this instance, but then there's been an erosion event because the basalt is not present. The basalt's been eroded away. And now we're down into unit 9 of the gold mold dolerite, and we're depositing conglomerate and dolerite debris on top of that. So that's whether or not that's one of these regional unconformities that are critical for gold in and around this district, I'm not sure. But in this instance, it's a very different upper boundary for this dolerite. Righto, just a bit of a break and something different. There's the Devon Consols basalt. I include it here just because it's unusual to get a really good photo of this thing. So it's a nice clean image there on the right. And I was able to link that with a document we trawled up quite by accident in one of the libraries that shows the formation of the ocelli and the different, just the geometry of those structures as it sits there in the rock. So I've never really worked out a nice, neat reason why this forms, and there's the very deep texture and the ocelli is a couple of different explanations for it. But I give you this image here, use it, abuse it. It's just, it was just neat to finally get one that's decent. And again, with the Hannans Lake serpentinite, in this instance, it's been altered. So the chrome in the ultramafic or in the komatiite here has been reacted, and it's given us a chrome cerussite, so fuchsite. So we often see fuchsite in and around the district, and whether it's in a lode that's passing through the ultramafic or in the black flag beds where you're getting pieces or bits of debris of the underlying rocks that have been eroded and washed into those older basins. You see the fuchsite, it's very visible, even in weathered rock, it still retains its colour. So it's easy to identify. You're always double checking yourself going, is that malachite? I'm not sure, but you check it and it's like, yeah, sure enough, it's fuchsite. Yeah. Another unusual thing we came across, we were out looking at long drill holes that have tested further away from the main mineralised system, and there's a series of holes sitting out to the east, and they go underneath some of the tails dams or the dumps. And it was unusual looking through them. All of a sudden we get this Skarn Alteration in the dolerite, and it's got a particular, it's a very orange garnet, so maybe spessartine, so it's the manganese garnet, right? Linked with abundant carbonate, epidote, and it was just really odd. And it was just in these holes that were sitting out there. And I thought, oh, it's unusual. I have to come back to it one day and have a think about it. I mean, we'd seen similar things down near Fayetteville to the south. And then once I'd worked at St. Ives, it was not uncommon to find areas with these orange garnets. So there's an example there in the bottom part of the screen. Orange garnets with the same alteration. In this instance, rather than being a dolerite, it's in a basalt. So it's just odd. It's something I've never been able to run to ground, but just put it here so people can see it and be aware that somehow this is part of these mineralising systems. And I think the manganese is probably part of that story. So copper is what you don't really expect when you're talking about an orogenic gold system. So in this example, I'd taken my daughter out to have a look at the super pit after a particularly big storm. We thought, oh, the walls will be washed down. We'll be able to see all sorts of things and maybe see some trucks sliding around. It'll be good fun. And she was up for it, so off we went. And we're standing on the pit wall, and we could see green over near the Golden Mile Fault, and it was quite abundant amounts of green. It was really obvious. I was like, oh, I have to go and see what that is. That's unexpected. So next couple of days when it dries up, we go out there and have a look. And sure enough, there's plenty of green coming out of the walls. So there's the fluffy sort of junk sitting there in the second from the right. That's chalcanthite. So it's a form of copper sulfate, not unlike blue copper sulfate you're familiar with from school. But then there's proper malachite there plating out. It's coming out of the black flags, out of these black shales in that sediment sequence. So there's obviously an appreciable amount of copper minerals kicking around in that system. And I recall the doré bars were usually enriched in copper. So it was, not unexpected when you think about it. I also recall when we were mining down through the Golden Pike on the western side of the deposit, and the upper portions, we came across, pockets of malachite up in the oxide zone. So it's two examples there in the lower part of the screen, the malachite. So there's obviously appreciable copper being kicked around over in that part of the system as well. So it's not to be ignored. It's out there. It's probably an issue for your metallurgists as well, but it's part of the system, and it's something to be aware of. So this was a surprise, and we came across it because one of the younger geos just mentioned in passing something about, oh, I'd seen some fuchsite chips in the paleochannel. I was like, what? Doesn't make any sense. So anyway, the other geos went and had a look, and sure enough, they said, no, this is copper. We've tested it, and you can see the knife blade there, the copper test. So just acidify it, and that plates the copper out on your blade. It's like, sure enough, that's just proof positive. It can't be anything else. I was like, right, that's really weird. So this example is STGD2. So this holds out under Hannon's Lake, down towards Hannon South. So it may or may not be associated with the Hannon South deposit, which is known to carry some copper. Well, there may or may not be another deposit nearby that hasn't been found yet. But this is a very unusual occurrence. And I have seen something similar in South America when I went to visit the Spence deposit. So that was found by a geo who was, alert at the time and spotted malachite in the transported cover as they're drilling through it. They're doing very broad-spaced RAB drilling. I think from memory it was 2 kilometre spaced holes. So just happened to pick up a chip of malachite in the sieve. And the rest is history, right? So here we have fragments of copper in the paleochannel. So somewhere in the drainage catchment of this ancient river, there's a deposit that's shedding copper. And it's not isolated. Like here's another example. So this is an EIS hole sponsored by the government. So it's in their collection. This is out at Golden Mile South. And again, in this example, there's no shortage of copper fragments in these transported sediments. And again, test it, proof positive, it's copper. So these are real. Exotic copper kicking around in and around these mineral systems is a very real thing. So going on with the theme of clasts, mineralised clasts are always really interesting because the observation is you have a clast in a rock mass. The rock mass itself isn't mineralised, but individual clasts within it are. So what's happening is there's a mineralising system that's earlier. It forms the mineralisation, which is then eroded, forms the clasts get deposited into a basin. So that's what we're seeing. So again, somewhere in the catchment back in the day in this very ancient basin, there's something that's mineralised and shedding mineralisation as clasts. So that's a really interesting thing. So to be able to try and track this back to its source would be really something. But again, that's a bit beyond me. Here's another example of that story. So this one's from up at 8 Mile Dam to the north of the system. So the sediments here, generally coarse sandstones to conglomerates, and it's dominated by porphyry clasts. So these porphyry clasts in this example, they're altered. The rock mass is less so, and the alteration and veining just crosses across individual clasts, right? So it's occurred before this thing was eroded and rolled into this basin. In this example, this rock, we had these very fine veins going through this clast, and this is the large clast in the center of field I'm talking about. So there was thin stringers of chalcopyrite running right down the center of these veins, and the occasional piece of visible gold. So it was really something. It's tantalizing knowing somewhere again within the catchment area of this rock that there's going to be a deposit, potentially a porphyry copper gold deposit, sitting out there somewhere in the vicinity of Fimiston. And how we would find that, I don't know, right? But it's the evidence for it exists here in this drill core from this ancient basin. And again, a similar thing. So this was SE18 hole drilled to the south of the Golden Mile, out near on the edge of Hannon's Lake. And this example here, so it's down around 1,270 metres, give or take. And we've got a conglomerate unit, and it's got clasts of dolerite in it. And it's also got clasts of massive sulfides. So it's sphalerite, pyrrhotite, chalcopyrite. There was even a bit of galena in there. And all these things are being eroded off some pre-existing mineral system and being washed into this particular part of the basin. So it's the same story as before. There's some other system nearby, and it's not Fimiston, right? Something else is being washed into here. So there's plenty of other deposits to be found in and around Kalgoorlie. We just need newer ways to track these things back to source. Going with the base metal theme. So this is a little trick, a rule of thumb that I was taught by a geologist. His name was Peter Sporer. He's passed away now. But, he was very helpful, not just to myself, but many other geologists. So he's well liked and remembered. In this example, we've got quite a bit of visible gold in this sample. So this is a quartz vein, a Charlotte style quartz vein, and it's cutting through a piece of Paringa basalt. So one association we noticed, so blackjack, so very dark sphalerite. When you got an increase in the concentration of the sphalerite, you would almost always find chunks of gold sitting in and around it. So that's one thing Peter taught me. He said, if you're trying to find a piece of visible gold, so you get a spectacular sample, you can put down on the desk of the exploration manager. He says, the first thing you do is you start looking for your sphalerite and galena, and particularly galena. And he says, once you've found that, the visible gold is right next door. It's easy to find. So the base metal sulfides are very easy to see. And then once you hunt around near that, you'll find the visible gold. And it's always worked for me. Like every time you visit a deposit, you use the method and bam, you find yourself a decent sample. It's like, right, look at that. So anyway, that's just a little aside. So, looking at the different base metals or tellurides in this instance, this was another little learning. We had this sample that we drilled up. So it's actually a piece of drill core, and we're fairly convinced we had telluride. And I needed a method to test it. And this before, again, we had the ray guns. So I've been talking around with a bunch of prospectors in Cal, and they'd convinced me, it's fairly easy to test for the presence of telluride. You use stannous chloride. So, right. So I didn't do any other research than how to make stannous chloride. So I went and got a piece of solder and dissolved it in acid, hydrochloric, and boom, you're supposed to get stannous chloride solution, but I didn't. It was a complete mess because the lead in the solder reacts and clouds your solution and it's junk. Sorry. Do a bit more reading. All right, so I've got to go and get a high tin solder, probably with antimony instead of lead. So give that a go, and sure enough, it works. Filter it off, get a nice clean solution, and you put it in a little jar and protect it because UV light destroys it. Went and grabbed a few little bits of this mineral and put it in the beaker, so you can see the little fragments there in the bottom of the beaker. And gave it a bit of time because nothing happened. So came back to it the next day, and sure enough, the solution had turned a pale purple colour. So this is the purple of Cassius. That's the result of this chemical test. So I was pretty excited about that. So I went off and telling everyone and spoke to the Mets, and the Mets are, poking fun at me. He says, "You don't know what you're doing." I was like, "Yeah, fair enough," but I gave it a go. And they said, "You're not seeing tellurium, you're seeing gold." I was like, "What?" So the test using stannous chloride tests for the presence of gold, not for tellurium. Oh yeah, okay. So then went and did some proper reading and, learned everything about it. I was like, right, okay, all right. So the key take home was, for all the wrong reasons, I found out that this piece of galena was carrying gold. And that was really quite something because we weren't expecting it. But it also sort of links back to that concept of look for galena and you'll find your gold there. All right, leucoxene alteration. So whenever you're exploring, certainly around Kalgoorlie and further afield across the Yilgarn, and it probably holds true for all the other greenstone fields around the world, there's leucoxene alteration is something that's you want to see. It's a key part of the system. And I always had trouble trying to wrap my head around what's going on and where's it at. But we're able to solve that and understand it. And you guys who are listening probably, know it and think it's all very self-evident, but it wasn't at the time, so we just had to fumble our way through it. So originally we thought you have a structure, the fluid gets in, the alteration leaks out, and it precipitates out these unusual titanium-rich oxide hydroxide accumulations, right? But this isn't the case at all. The fluid gets out, but it reacts with the pre-existing magnetite in the rock. And when it does this, that reaction destabilizes the fluid, and any other metals or other minerals that are being carried in the fluid, they precipitate. So it's this reaction that drives the formation of these gold-bearing structures in and around, in this instance, Kalgoorlie. So what we see here, these white minerals, is the leucoxene, and essentially they have the dendritic and cubic bipyramid shapes that are fairly typical of magnetite. So in this instance, it's probably not a pure magnetite, it's an extremely titanium-rich and probably a vanadium-rich magnetite. So when you break it down, you're left with the titanium oxide hydroxides giving you the leucoxene, and you liberate the vanadium. The vanadium goes off and does, whatever it wants, forming, bright green micas as an example. But I'll just run through a few magnetite examples because it'll help, understand. So this example here is from hole jug 11. This one's been delivered to the government library because it's an important one. It goes through all of the units of the gold mold dolerite, and they're easy to see and easy to understand. In this example, we have very coarse grains of leucoxene, so it's nearly 3-4 centimeters across. So that dendritic crystal in the middle of the field used to be magnetite. So it has a magnetite crystal structure, but it's just been converted now to these titanium oxide hydroxides. And you can see There's other crystals in there as well. You know, there's plenty of them. But just this is a very large example, and it's easy to see. Yeah. And this one here, LF7, is where it was really obvious. So you can see the alteration front on the left image is just encroaching on that dendrite. So it's starting to go pale, beigey colour. And the image on the right, it's completely converted to leucoxene. And you'll also notice that the pyrite is crystallising hard against the side of those dendrites. So these dendrites, by virtue of their enormous surface area, are very receptive to this alteration, and it helps drop out the sulfides and any other gold and metals that are kicking around in those mineralizing fluids. Yeah. And another example, so here's these classic early Fimiston style veins. So it's the coliform cockade textures, and the dark material in the center there is particularly magnetite rich. So example there, that piece of rock upside down, the magnetite sticks, yep, it's magnetic, right? So it's the observation is extremely magnetic, and that magnetite alteration is linked to the very early Fimiston events. So it helps to essentially prepare the ground. This particular sample is chock-a-block full of telluride. It came out of the open pit at Fimiston. I wish I'd got a location on it because it's a very important sample. So this one, that center of the field, you've got a very large bipyramid of magnetite, and it's intergrown there with the telluride itself. So this crystal grew with the mineralization. So it was very confusing at first, but I worked it out in the end. Is mineralizing event occurs, it consumes the magnetite in the rock, and then it reforms a different sort of magnetite as part of the mineralizing event. And that's one way, or a very simple way, to explain what we see. And that observation is the magnetite intergrown with the ore. So here's another example. So looking at that sample on the left-hand side, the one that's extremely bandy. So the black spots sitting probably in the middle of that sample in one of those bands there, they're magnetites. So these magnetites have grown, even though that rock's altered, they haven't been consumed. So these are part of that secondary magnetite event. So even though you consume the magnetite, you make the rock not magnetic, you reform magnetite and take it back to being very magnetic rock. And it helps explain why you've got this huge mass of rock that's all altered and it retains its magnetic character. Yeah. Interesting thing is these bandy veins, these vein textures, in all three of these samples, there's coliform cockade textures, and in between those banded silicates and carbonates, you tend to get chalcedony. So again, that chalcedony forming probably from colloidal solutions at low temperature and low pressure. And the interpretation is that's occurring near or at the surface of the Earth. This rock was a particularly good lesson, not just for myself, but for the entire geological team. There was a tradition, I guess. You'd have people would go, all right, very quickly try and grade control something. It's got coarse-grained pyrite, and it's quartz carbonate vein within the dolerite. And the thinking was that these type of veins and this type of alteration was barren. This was challenged by one of the field assistants, or the senior fieldy actually. He said, how do you even know? If you're not even sampling it, how do you even know? And it's like, oh, no, the guys, it's always barren. It's like, so anyway, I thought, it's a fair question. That really is. So we assayed it and it came back running 8 grams. So lesson was, don't just assume it, measure it, take the sample, test it, get the result, and then make your decisions based on that. Yeah, so that was a good lesson. That's why I kept this image. It's always a good reminder, is assay your rock, don't just guess. Alrighty, so here we are back to the ad. Just to remind everyone, Carl's waiting now. He wants your emails, he wants your papers for this new volume of critical minerals, because I'd like to read it, as do all of you. So get in touch and write some papers. So just a conclusion, just a quick recap. It's being clear what's an observation interpretation. I mean, almost every time you get mixed up is when you've interpreted something beyond your observations. You just start making all these assumptions, and then off you go, you make assumptions on top of assumptions, and you get it wrong. So you just got to be quick to correct, go back to your observations and see where you stand. Persisting, as always in exploration, it gets you there. You're going to get knocked back on all sorts of things. You'll get it wrong. Let's just have another go and you'll work it out. Taking those routine observations over time, it gets you where you need to be. And you might just be doing dips and strikes routinely every day, over and over and over. But over a period of time, you end up with this enormous map and you understand the trend of everything. You understand what's going on structurally, you know. And finally, trusting your observations. You know, ahead of the interpretations, when people are telling you this is the case, but where's the evidence, right? So go and look at the outcrop. That's and these subtle little things that you do, they matter, right? You take simple observation, it leads you to the right answer. And certainly the observations you make, you'll make observations and you think, I don't know what to do with this. But you just got to put it to the side there and just keep it and go, one day we'll come back to that. It could matter for something, you know. You've found a clast in a basin that's mineralized. What does that mean? It means something, but, you know, we couldn't work it out at this time. Yeah, no worries. I'll just leave you with this nice high-res scan of a piece of rock. Thank you.